Alright, time for another DraftPhysics.com video presentation. So, a response again to physicist Michael. I'm going to provide a counter experiment, an experiment that isn't consistent with your experimental results. Now, it's not the same experiment, unfortunately, but it is an experiment that demonstrates clearly that momentum does have to be conserved, and I can't change how much momentum a spring produces by merely putting more mass in front of the spring. I can't change it. It will conserve momentum. Alright, so this is a South African video. I have played it in the past quite a while ago. I mean, it does show conservation of momentum, and it does show that kinetic energy is destroyed. So you start with a certain assumption about what the spring contains. Clearly the spring will make more kinetic energy in one experiment than it makes in the other experiment. So it's a counter argument to your experiment. It's an experiment showing a different result, that the kinetic energy isn't conserved and the momentum is.
Today, our task is to investigate whether the principle of conservation of linear momentum holds true for an explosion, which, as you know it, is inelastic.
So spring is being called an explosion. Now that's a little bit tricky, right? Because I would argue that, yeah, it's not quite the same thing. The spring can be suspect in terms of, how exactly it distributes its energy. It's not as consistent, you'd argue, as an explosion might be. Because of the irregularities of even temperature, different things can affect it. Now, I guess you could argue that those same things could affect dynamite or something like that. And it's really this hitting mechanism, right? This is a plunger compressed into a spring, and it clearly could end up hitting the cart rather than pushing the cart. So there are some catches to the experiment, but I don't think they're that important.
Two trolleys are placed on a track and released by a spring. They move in opposite directions.
Before the explosion, both trolleys are at rest. They have zero momentum and zero kinetic energy. After the explosion, they have kinetic energy and momentum. Kinetic energy is not conserved during an explosion.
So, they're clearly saying, as Professor Lewin said, nature can finagle kinetic energy, but it can't finagle momentum. So, no matter which cars fly off, the total momentum has to be conserved. The spring will produce a certain amount of momentum. It has to produce that much momentum no matter what I put here. 2 heavy carts, 2 light carts. It doesn't matter what I put in front of that spring. The things will be pushed, conserving the momentum. Your experiment shows exactly the opposite. You showed kinetic energy being conserved and momentum being destroyed. So it's clearly this experiment disputes your experiment. So which one do I believe and which one do I say is suspect? Well, first I'd say this one is kind of obvious and more upfront. I mean, in the sense that it's kind of obvious what takes place. You're not relying on instruments telling you what the speeds are or any of that other stuff. You're visually seeing it.
Therefore, an explosion is inelastic. The question we are investigating is, does the principle of conservation of linear momentum apply to isolated systems during inelastic collisions and/or explosions?
The apparatus for this investigation is an almost frictionless track, 2 trolleys, and some extra mass pieces. 2 stoppers at each end of the track.
Alright, so I think they're going to go into a whole bunch of crap about leveling the track. Yeah, we don't need all that. We don't need all this other crapola. So we'll get to somewhere around here. And they should be getting close to doing the experiment.
And to hit their stoppers at exactly the same time. Let's try it first with 2 trolleys of equal mass.
It makes sense that the trolleys of equal mass accelerate at the same rate when the same force is exerted on them.
Alright, it also makes sense that if I put 2 100 mass carts, and then I put 2 200 mass carts, and then I put 2 300 mass carts, that yes, I will get the same total momentum out of the system. It's a closed system, a closed spring, the same compression. I should conserve the momentum by what the rules of physics say. So my argument is physicist Michael has established that he has proven, and it's an unassailable experiment, it's proven that that isn't true, that momentum can be destroyed. I can just wipe it out altogether, or I can make free momentum, however you want to look at it, that the spring is completely variable in what energy it will produce. That's his proven factual argument that cannot be disputed. I'm saying this experiment disputes it.
That is what Newton's second law tells us.
So, the two trolleys will have the same final velocity as they travel down the track in opposite directions. They hit the barrier at the same time if they travel the same distance.
So we position the two trolleys of equal mass in the center of the track. Measure the distance from the front of each trolley to the stopper.
Yes, yes.
And we release the trolleys from their positions.
The mass of each trolley equals 250 grams. The distance of the red trolley to the stopper is equals to 63 centimeters. The distance of the blue trolley to the stopper is equals to 63 centimeters.
Now this experiment would be excellent if they actually timed it. So if I could probably do it, frankly, okay? I could go to the trouble, but I don't know if it's worth it, of timing how long it takes them to hit the barrier. And then we can see, because they're going to do it exactly what he did. They're going to make the carts twice as heavy and then do the same experiment. And you'll see that they're moving much, much slower. Now we don't have the exact numbers.
Yes.
And we release the trolleys. Listen carefully. The trolleys must hit their end stoppers at exactly the same moment.
So that's the speed of the half-mass trolleys. And then they're going to do it with twice as heavy trolleys. And it's going to look a lot like twice as long.
Try this again, but this time we add a mass piece to each trolley. Remember that each mass piece has the same mass as the trolley. Each has a mass of 250 grams. Measure the distance from the front of each trolley to their stoppers.
The mass of each trolley is now 500 grams. The distance of the red trolley from its stopper is 63 centimeters. And the distance of the blue trolley from its stopper is 63 centimeters.
Release the trolleys and listen carefully.
Listen to how long it takes. Much longer.
They hit the stoppers at exactly the same time.
Now what would happen when one of the trolleys is twice the mass of the other trolley?
Right, so this is the important one because it's visually in your face in the sense that it's obviously conserving the momentum. So they're going to put twice the mass on this little red cart that the blue cart has, and it's going to show that they both have the same momentum, and clearly going to show that one cart has more kinetic energy. So kinetic energy won't be conserved. That is, you'll have the same kinetic energy in one direction in the previous experiment, but you won't have the same kinetic energy in the other direction. So it will not conserve kinetic energy, and it will in fact conserve perfectly momentum because it will be exactly, proportional. The velocity is obviously 1/2 the velocity. It's a mathematical proven fact that it will be 1/2 the velocity. So the twice as massive cart will move half the speed. Okay, not some other speed. Half the speed. And so this kind of goes to the Professor Lewin experiment because frankly it's it's just another version of it. You're smashing a 1-mass cart into a 2-mass cart. And it doesn't matter which one's hitting which. You're just asking what happens to the momentum. Is the momentum conserved? And the fact is the momentum has to be conserved. So whether I compress the spring and launch the objects or whether I bang the objects into each other and compress the spring and launch the objects, it's really the same result. And you have to conserve the momentum.
Let's make the red trolley twice the mass of the blue trolley.
We need to find a position which allows them to both hit their respective barriers at exactly the same time.
We could try endless possibilities by trial and error, or we can work out the correct starting position for these trolleys. We can use the principle of conservation of linear momentum.
Applying the principle of conservation of momentum, we know that the initial linear momentum of the system is equal to its final momentum. Therefore, 2mv red is equal to minus...
So this is the part that's really kind of irritating, right? Because they do this 0 plus 0 thing. But what they know is they put a certain amount of force into the spring. It took a certain amount of force to compress the spring. So they know it's a specific amount of energy that they put in. And there's a specific amount of energy they can expect to get out. And that's the simple truth. And it's just this way they do this, where they pretend they didn't put any direct energy in. When they directly did it, they pushed the spring. I mean, they did it. They physically did it. So why are we pretending this is about things with zero? These are things that have, obviously, potential. And you can release that potential. So why are we pretending this is a zero-sum game when it is, in fact, real motion? And it's real energy. And you can't subtract it. The red car is not going to subtract the blue car. They are now energy revealed, both of them.
mv blue. Dividing through by the mass m, we get 2v red equals minus v blue. But delta t is the same for both trolleys. Therefore, 2 delta x red is equal to delta x blue. Delta x red is equal to half delta x blue.
So because it's half, you have to understand that it's going to have more time. The red one is going to have more time to hit. So you have to give it more distance. So you have to not slide. You don't slide to 1/4, you slide to 2/3.
The red trolley has twice the mass of the blue trolley. Therefore, the red trolley accelerates at half the rate of the blue trolley. It covers half the distance of that the blue trolley covers in the same time.
We need to divide the track into thirds.
And so there will be, no conservation of kinetic energy in the sense that the one car will have more kinetic energy than the other car.
The trolley of the greater mass will travel 1/3 of the track, while the trolley of the lesser mass will cover 2/3 of the track, so that they both hit their stoppers at the same time.
Right, let's position the trolleys more carefully. Measure their distance from their stoppers. Remember that the distance of the trolley must be half as much as the distance of the blue trolley for this to work out.
The mass of the red trolley is 500 grams, and that of the blue trolley is 250 grams. The distance of the red trolley from its stopper is 42 centimeters. The distance of the blue trolley from its stopper is 84 centimeters.
Perfect. There.
Yeah. So perfect in the sense that you have more kinetic energy going one way than you have the other way, so you don't conserve kinetic energy. I would argue also perfect in demonstrating that there isn't more kinetic energy going into the heavier object. There's not more energy, period. I mean, more momentum. So they can say it, but it didn't happen in the experiment. There's not more energy in the red cart because it's heavier. It didn't absorb more energy. It got half the momentum. So again, I said energy, and that's going to confuse you because you think kinetic energy is what I'm talking about. No, I'm talking about it didn't create more. There's not more momentum in one cart than the other cart. They both got half the momentum. So obviously putting heavier things in front of a spring does not make the spring create more momentum. So if you do an experiment where you put one mass on the spring and it creates a momentum, and then you put a 2 mass and it creates a different momentum, something's wrong with your experiment. That's what this experiment demonstrates. So I guess we'll just leave it at that and see if he has a counter argument. Again, I wish they had done the timing thing. I mean, maybe, like I said, if you're going to keep arguing the point, it might be worth measuring how long it took the carts in the first experiment to hit the bumpers, and then measure the time it took for the second carts, the heavier carts, to hit the bumpers. And if those two aren't the same, then we can say springs don't conserve momentum. But if those times, okay, are exactly half, because you have twice the weight, then it proves that the momentum of the spring is conserved and that your experiments have a flaw in them. Can't really say it any other way. I mean, you can't reverse your experiment. I can reverse these experiments and get the same spring compression. I can't reverse yours and get the same spring compression. I shouldn't have to argue any further than that. It's a decisively relevant and poignant argument. And you have to come up with some sort of explanation of why the spring is able to produce different momentums. Where did the momentum go? All right. You clearly didn't conserve it. Say the words. Springs don't conserve momentum. Please, say the words. Okay, I guess that's all. All right, so we'll just keep it at that. It's just for the purpose of this one argument about his experiment and the fact that he got results that, in my opinion, are not consistent with other experiments and not consistent with the laws of his own physics. Yeah, enough said.